Part 3, Standard Limit Results. So in this class we will actually learn some results which you would need to by heart if you have to do problems with ease. So I recommend you actually get to understand it and then by heart it, but you would need these results in upcoming problems and the ones that come for your exam. So let's get started. This class is mainly on by hearting stuff, so cope with me because I'm not the best by hearter and I don't expect you to do so. I want you to really understand what these limits are and then you can mug them up. So standard limits are well-known limits that have fixed values, often derived using advanced tools like L'Hopital's rule or Taylor sequence. So we don't have to really dive deep into that. We just know that these limits have been derived by other mathematicians using different rules such as L'Hopital's rule or the Taylor series. So let's get to know what these limits are. We can group them into two types of limits. We have the trigonometric limits. We know what trigonometric ratios are, sine, cos, tan. So with those we have some limits. And then we have the exponential limits. There are so many other more results, but for now this will do. So let's discuss trigonometric limits. First of all, we have first result, limit x tends to 0 sin x divided by x is equal to 1. So the first result is limit x tends to 0 sin x by x is equal to 1. So for a function sin x divided by x, when x is tending to the number 0, the result would always be 1. So we don't have to prove this, but I'll tell you, if sin x, if we actually give the value for x here, sin 0 by 0 would equal to 0 by 0. So if we get a 0 by 0 form, suppose we get a function which evaluates to 0 by 0. For that function, we can apply L'Hopital's rule. So that's where this comes from. L'Hopital's rule is where we can derivate both the numerator and denominator. So if we derivate sin x, we get cos x. If we derivate the denominator, we get 1. So if we apply the limit on that, we get limit x tends to 0 cos x by 1, and then we apply the limit cos 0 by 1 which is equal to 1 by 1 which is equal to 1. So that's how we actually get this result. But for now, if you don't know differentiation, don't worry, but we'll learn it in upcoming classes. But for now, this is the limit, and you have to understand that this came from another rule called L'Hopital's rule. Second result, it's very similar to this except it's for tan. Limit x tends to 0 tan x divided by x is equal to 1. So this came from the same thing, but here instead of sin x we get tan x. So for sin x and tan x, if we get this format, we can just evaluate it to 1. Third result would be for cos, but this time it's a little different. X tends to 0. It's really easy to identify because x is always tending to 0 for all these results. 1 minus cos x divided by x is equal to 0. So here 1 minus cos x divided by x when x tends to 0 is 0. Fourth limit x tends to 0 1 minus cos x, but instead of x in the denominator we have x square. So this will change it up, we get a fraction 1 by 2. Okay, so the first two and last two are a little similar. For the first two we have sin x and tan x, and both of them evaluate to 1 in this same format, sin x by x or tan x by x when x tends to 0. And the last two we have 1 minus cos x, but in the third one we have x as the denominator, and the second one we have x square as the denominator. This changes the result. In the first one we get 0, in the second one we get 1 by 2. So these 4 trigonometric limits you have to actually by heart. Now the second set of exponential limits. Exponential limits include first one, limit x tends to 0, e raised to x minus 1 divided by x is equal to 1. So you probably may or may not have heard of e. E is called Euler's number, and it is almost equal to 2.71828, etc. So e is called, it's a constant, it's called Euler's number, and it's used as the base of natural logarithms, which you probably haven't learned. But for now you understand that for the function Euler's number raised to some x minus 1 divided by x, when x tends to 0 we get the value 1. And for the second one we have limit. This is really similar to the one, but instead of Euler's number we actually write a raised to x. For a is any number and x is a variable, by x is equal to natural log of a. Okay, I'll tell you what this is. Natural log of a, or we can write it like this, log to the base e of a. Okay, so these two are really similar. Instead of a you put e and you get 1. I'll tell you how that happens. If you put e instead of a, you get the result as ln e, right? If you put e instead of a, and natural logarithm of e is 1, because log and exponential function are inverse functions. So if we write log to the base e of e, that would be equal to 1, because e raised to 1 is also e. This is a little tricky. Log to the base b of c is equal to a. If that's the case, then b raised to a would equal to c. I've used the same concept here. If log to the base b of c is equal to a, then b raised to a is equal to c. In the same similar case, log e to the base of e is equal to 1. E raised to 1, that is b raised to a, is equal to this number, which is e. So we can write, so since this is 1, this would be a special case of this general result. So you just have to by heart this, and you plug in the value e, and we know ln e is equal to 1, so we get this result. So we have to study all these results, and this little logarithmic trick is quite useful to keep in mind. Log to the base b of c is equal to a, then b raised to a is equal to c.